A very good day to Dr. Rahifa. My name is Lu Wei-jun and today I will present the group assignment for Engineering Mathematics 2. Before I start first, let me introduce my group member first, which is me, Yam Zishan, Wong Kolong, Sudaga, Anak Laki Langgo, and Teo Lindsay. So the question 1 is that a rectangular electric burner plate of the region with limit x is 3 to 1, limit y is pi over 4 to negative pi over 4 is heated so that the temperature at the point xy is 4x minus x squared times cos y. So we need to find the temperature at the hottest and coldest point on the electric burner plate. The method we use is the local extrema method. Before we start, first we need to find the derivative of temperature with respect to x, y, xx, yy, and xy. So this is the answer for the derivative of temperature. In order to find the critical point, the derivative of temperature with respect to x and y must equal to 0. By using the substitution method, we find that the x is equal to 2 and y equal to 0. So this is the critical point. After that, we need to verify this critical point is local maximum, local minimum, saddle point, or non-convolution first. So we sub the critical point to the temperature with respect derivative of temperature with respect to xx, yy, and xy. So we will get this answer, which is -2, -4, and 0. We sub these three answer to the formula and we'll get that the answer is 8. After that, we can get a conclusion that this is more than 0 and the derivative of xx is less than 0. We get the critical point is at local maximum. By substituting this critical point to the temperature formula, we'll get that the temperature at the highest point is 4 degrees Celsius. After finding the highest point, we find the coldest point, which is on 4 corner. So we know that the limit of x is 1 and 3, the limit of y is pi over 4 to negative pi over 4. So this 4 point will be the coldest point, which is the local minimum. By substitute the x equal to 1 to the temperature formula, we will get that the answer is 3 times cos y. The local minimum at y is equal to plus minus pi over 4. By sub this answer to the temperature formula, we'll get that the temperature at the one of the corner is 3 over square root 2 degrees Celsius. After that, we find the temperature on the line x equal to 3. After we sub the x equal to 3 to the temperature formula, we will get that the answer is 3 cos y. Since we know that the local minimum at y is equal to plus minus pi over 4, we will get that the temperature at this point is 3 over square root 2, which is same as the previous answer. And the other point for the local minimum is y to equal to plus minus pi over 4. By substitute this answer to the temperature formula, we will get that the answer is 4x minus x squared over square root 2. Since we know that the local minimum at x is equal to 1 and 3, so we will get the same temperature, which is 3 over square root 2 degrees Celsius. So in conclusion, we can know that the highest temperature for the answer is for the absolute maximum is 4 degrees Celsius, and we know that the coldest point at the plate is 3 over square root 2 for this question. That's all for me. Thank you.
A very good day to my lecturer, Para Rahifa, and my fellow friends. So my name is Yap Zushen, and today I'm going to proceed with our group's assignment question 2. So for question 2, the question wants us to find the centroid for solid G, and the formula to find the centroid for the solid has been given as shown in the slide here above here. X bar equals to 1 over v triple integral x dv, y bar equals to 1 over v triple integral y dv, and z bar equals to 1 over v triple integral z dv. And the solid G is bounded by above by the sphere with radius 4 and below by the cone z equals to square root x square plus y square. Based on the above formula, find the centroid of solid G. Okay, so for this question, first we have to sketch out the solid G based on the equation given. So here will be the figure for solid G as shown here, and it's going to be like a ice cream cone, and yeah, bounded by sphere with radius 4. So the first half of the sphere will be here with a radius 4, and below will be the cone, which is the equation z equals to square root x square plus y square. So now I'm going to write the limits for the solid G here. Rho, we know that rho is basically the radius, which is 0 to 4 based on this sphere. And then for theta is going to be the angle between xy plane. So as we can see here, the xy plane is basically 360 degrees. So the limits for theta is from 0 to 2 pi, and for phi it's going to be the angle from the z plane, which is 45 degrees. So we're going to put the limit for phi 0 to pi over 4. Okay, next we're going to solve the volume for the solid G, since V is required to solve the centroid of solid G. So first we have to convert the formula from Cartesian plane into spherical plane. So we're going to obtain a new equation, which is V equals to triple integral rho square sine phi in terms of d phi d rho d phi d theta, and we just plot in the limits we obtained just now into the volume equation, and yeah, after that we just solve the integration like how we usually do, and we're going to get the answer of 2 pi times 64 over 3 minus 32 times 2 over 3. So this will be the volume for solid G. So next we're going to find the volume in the YZ plane, and similar like just now, we're going to change the formula from Cartesian coordinates into spherical coordinates first, and we're going to obtain a brand new formula, which is triple integral rho sine phi cos theta times rho square sine phi d rho d phi and d theta. And same like just now, we just plot in the limits and then solve the integration like how we usually do, and we are going to obtain volume in YZ plane is equals to 0. So that here's a side note, we are going to require to use the trigonometry identities to solve this integration, which is sine square theta equals to 1 minus cos 2 theta over 2. And yeah, we're going to use this identity inside this part of integration here, and then we just solve it like normal. We're going to get 0. For volume in terms of xz plane, we are going to change it to from coordinate plane into spherical coordinates, which is triple integral rho sine phi sine theta rho square sine phi d rho then d theta, and then we just solve it like normal, and we are going to get 32 minus 16 pi. And last but not least, we are going to find the volume in xy plane, and same, we just convert the formula from rectangular coordinates into spherical coordinates. We're going to get a new formula of triple integral rho cos phi rho square sine phi d rho d phi d theta. Just put in the limits we obtain from solid G just now, and then we just solve it like normal, we'll get 32 pi. Okay. So now, based on the question, the centroid for solid G can be obtained by these three formulas here: x bar, y bar, and also z bar. So basically, this thing here is just can be written as volume in yz plane over v for x bar. Y bar is equals to v in xz plane over v, and volume in terms of xy plane equals to vz over v. So we just plot in the values we found just now, and we are going to obtain the centroid for solid G. For x bar, we're going to get 0. For y bar, we're going to get negative 0.4652. And lastly, for z bar, we are going to get 2.561. So this will be the centroid coordinates for solid G.
Good morning, my name is Ong Kolong. I will present about the question 3. So the question 3 needs us to verify the Stokes theorem for the vector field F by given this equation. And the vector field is in the rectangular region in xy plane bounded by the line x equal to negative a, x equal to positive a, and y equal to 0 and y equal to b. In my part, I will present how my solution by sketching the rectangular region and explain how the line integral of vector field F is equal to surface integral of vector field F. First, I will sketching the rectangular region by using the information given by the question. So for the first point, x equal to a, y equal to 0. For the second point, x equal to a, y equal to b. And for the third point, x equal to negative a, y equal to b. And for the fourth point, x equal to negative a and y equal to 0. So we will sketch the rectangular region like this. And then next, I will find the surface integral. So before finding the surface integral, we need to determine the curve of vector field F by substituting the information inside the formula, and then we get the curve of vector field F is equal to 0. Next, since the curve of vector field F is equal to 0, and then the surface integral of vector field F will be 0. Next, I will find the line integral of vector field F, and then from the graph plotting we previous and be getting 4 paths. Which is the first path is from point A to point B, and the second path is from point B to point C, and then the third path is from point C to point D, and the fourth path is from point D to point A. So for the first path, the x remain as value a, and dx is equal to 0, and y is changed from 0 to b. Then we find the line integral of first path is equal to negative a and b power of 2. For the second path, the x change from positive a to negative a, and y remain as value b, so that the dy is equal to 0. And then we find the second path, line integral is equal to negative 2a over 3 plus 2y squared a. So next, we find the path 3. For the path 3, x remain as value negative a, so that the dx equal to 0 and y change from b to 0, and then we find the line integral of path 3 is equal to negative a multiplied with b squared. Next, we find the line integral for path 4, and then the x change from a to negative a to a, and y remain as value 0, and dy is equal to 0, and then we find the line integral for path 4 is equal to 2 over 3a power of 3. So lastly, we will find that we add all the four paths together and we can get the line integral is equal to 0. Last but not least, since the line integral is equal to surface integral is equal to 0, so the Stokes theorem states that the surface integral of curve of a vector function over a closed surface is equal to the line integral of vector function along the counter C bounding by the surface. So this is the explanation for the Stokes theorem.
Good day to Dr. Rahifa and my fellow friends. I'm Sudhagar Ilango and I'm going to present the application of Stokes theorem in electrical engineering. The application of Stokes theorem in electrical engineering is very important as it plays a major role in analyzing electromagnetic field. Analyzing electromagnetic field is vital in electrical machine design to design motor and generator. In this slide, we're going to calculate the flux of curl F across surface S below by using Stokes theorem. Note that the vector field is given. As we can see here, we have L1, L2 and L3. From point 1, to 0, 0, which is from here to here, we can find the gradient, which is equals to 1, and by using the equation y is equal to mx plus c, we can get the equation of that line, which is y is equals to x. Similarly, for the point 2, 0 to 1, 1, which is from here to here, for L2 basically we find the gradient is equal to -1, and with the same with the help of the same equation y is equal to mx plus c, we can get y is equal to -1 x plus 2, and we can rewrite this into x is equal to -y plus 2. Next, in order to use Stokes theorem, we need to first calculate the curl of E. For this, we are going to use this equation right here, this formula right here. Basically, this formula is the application of the concept of AD minus BC, where we do this for every vector x, y, and z. For vector x, we obtain 0. For vector y, we obtain 0 also, and for vector z, we obtain -3x, which in resultant yields -3x in the direction of vector z as an answer. Next, we're going to substitute this value into the Stokes theorem. So now that we have substituted the value -3x, we have to expand ds into dx dy. Now that we have expanded into dx dy, we have to put the limit of x first. The limit of x is from y to 2 minus y, and the limit of y is from 0 to 1. By solving this double integration, we get a final answer of -3.
Okay, so now we're going to proceed with question 4. For question 4, we are required to choose a topic which is related to what we have learned throughout the 14 weeks of engineering mathematics classes, and we have to write an essay about the application of the topic which is related to electrical engineering. So after having much discussion among the group members, we have decided to choose Green's theorem. Since Green's theorem has been one of the most interesting as well as most important theorem we have learned so far in our engineering mathematics classes. So Green's theorem allows us to determine and understand the relationship between line integral and also double integral. It provides us a way to determine the line integral of a smooth vector field F around a closed curve C, and R will be the region enclosed by the curve. As shown here in this figure, C will be the closed curve and R will be the region in between the closed curve. And Green's theorem is extremely useful, especially in electromagnetic theory and solving the applications related to EMT. So how do we apply Green's theorem? So basically, we can use Green's theorem to calculate the line integrals when C is a closed curve by using the formula below here, which is the double integral f xy in terms of dx plus g xy in terms of dy, which is equals to double integral partial differentiation of g in terms of x minus partial differentiation of f in terms of y over dA. And dA here can be dx dy or dy dx or r dr d theta. Depends on the equation given in the question, and we're going to choose depends on suitability lah. Okay, and here's some application for Green's theorem based on the information we have found online. So Green's theorem can be used to break down the line integrals into shorter paths, and it can be used to calculate the amount of work done on a force field, and it can be used to calculate the flux across a closed surface as well as water flow. So here's a fun fact. Normally in electromagnetic theory, we define flux as the number of magnetic field lines passing through a given surface. However, in engineering mathematics, we can use Green's theorem to calculate it by taking the line integral of vector field over a given curve. So before we look into an example for Green's theorem, here's a reminder that Green's theorem is only valid whenever the given curve is a closed curve. If it's not closed, then Green's theorem can't be used. So it's extremely vital to make sure that the given curve is a closed curve before we apply Green's theorem. So here's example 1, so which is related to calculation of flux. So for this question, we are required to calculate the flux of fxy, which is equals to vector x squared plus ey for I component and 3x plus y for j component across the curve C, where C is bounded by triangle 0, 0, 2, 0 and also 0, 4. Okay, so first we just sketch out the triangle as given as the given coordinates here, and as we can see here, it's basically a closed surface or closed curve. So Green's theorem can be applied for this question. Okay, and next we are going to have a look at this flux version for this Green theorem's formula, which is a little bit different from the general formula of Green's theorem. So for this flux version of Green's theorem formula, it will be double integral of partial derivative f in terms of x plus partial derivative of g in terms of y over a region R. This equation here is a little bit different from the general equation for Green's theorem, so please take note about that. And next we just apply the formula for the flux version of the Green's theorem formula. So first of all, we have to choose the f and g for the given flux vector. So for this question, we are going to choose x squared plus ey as our f and 3x plus y as our g. And we are going to solve del f in terms of del x. We are going to add 2x, and for del partial derivative of g in terms of y, we are going to get 1. So we just sub in both of these values here into the flux version equation just now, and just plot in the limits of this triangle, and then just solve it like normal. We're going to get 28 over 3. So based on the calculation shown, it can be seen that the flux of the vector field is found to be 28 over 3 units. Okay, so flux can be calculated with the usage of Green's theorem. So next we're going to have a look at our second example, which is the calculation of work done of a particle. So the question says that by using Green's theorem, calculate the work done of the particle if the given force field is Fxy, which is equals to y minus cos x in the I component and Ey minus 2x in the j component. Assume that the particle moves around in a circle represented by the equation x squared plus y squared equal to 9 in counterclockwise direction. Okay, so first we are going to sketch out the circle based on the equation given as shown here in this figure. So it's basically a normal circle with a radius of 3, and and the particles is moving in counterclockwise direction as shown here in this figure. Okay, so for this question, which is related to the work done application, we can use the general formula for Green's theorem, which is basically the double integral of partial derivative of g in terms of x minus partial derivative of f in terms of y over region A. Okay, so similar like just now, we are going to choose the f and g based on the given force field vectors. So for f, we are going to choose y minus cos x, while for g, we are going to choose ey minus 2x. And we are going to calculate del f over del y for y minus cos x, and we're going to obtain 1, while for partial derivative of g over in terms of x, we're going to get negative 2. And just simply plot in both of these values into the general equation of Green's theorem, and we just solve it like normal integration. And yeah, please take note that this question, since it's a circle, so we are going to use cylindrical coordinates rd theta, and just solve the integration like normal. We are going to get the work done equals to negative 18 pi. So it can be concluded that the total amount of work done on the particle is equals to negative 18 pi. So basically, Green's theorem can be used to find the particles work done as well. So yeah, that's it from our group. Thank you so much.